Okay, so today's topic is moving coil galvanometer. So we'll learn how to construct the galvanometer, then what are the working equations of galvanometer, and finally the two sensitivities related to the galvanometer. Okay, so let's get started. So in our laboratory, you will see instruments like this. So this is an emitter. So emitter or galvanometer both are used to measure current in a circuit, but galvanometer can only measure current in microampere. So the range of galvanometer is very small. So even if the current value of current is close to milliampere or ampere, then galvanometer will not be able to measure the current. So we use emitter when value of current is more. So galvanometer is used when the value of current is less. Less means in the range of microamperes. Okay. So how does a moving coil galvanometer works? So a galvanometer will give you direction of current. It will give you small magnitudes of current only in the range of microampere. And if we can measure I and if we have resistance R, then we can also measure voltages. So a galvanometer can give direction, can give value of current, and can also give value of potential difference. Okay, now it works on the principle that when a current carrying coil is placed in uniform magnetic field, it experiences a torque. Please remember this thing, that when a current carrying coil is placed in magnetic field, it will experience force. So our galvanometer works on this principle. So you can see the video now. So if you'll see in this video, then this is basically one side, another side. So a galvanometer has two poles, north pole, south pole. And this is how the magnetic field is there between the coils. This is how. So magnetic field is from north pole to south pole, and this is our coil. This is our small coil. Okay, so if current is passed in this coil, then this coil will rotate in magnetic field. So if current is passed in this coil, then this coil will rotate in magnetic field because there will be torque on this coil. Okay, now let's come to the equation part. So this is plane of the coil, and if you will see, the magnetic field is in this direction. So if you'll see in this figure, so this is the plane of coil. So I'm drawing again it like this. So this is the plane of coil. So area vector will be perpendicular and magnetic field is in this direction. So angle will be what? Angle will be 90 degree. So torque on a current carrying coil is mb sine theta. So on the place of theta, I'll put 90 degree. On the place of m, I'll put NIA. That is number of turns into current into area. So torque due to magnetic field will be NIAB. And also remember, this kind of magnetic field is known as radial magnetic field. So this radial magnetic field has two very important uses. First is it increases the value of magnetic field near the coil, because near the coil, if you see, the magnetic field lines are closer to each other. So more closer the magnetic field lines, more will be the value of magnetic field. And the second important use is to make theta equal to 90 degree. Because if theta is 90 degree, then sine 90 is 1, then torque will be maximum. So radial magnetic field increases the value of magnetic field and also makes the angle 90 degree between magnetic moment and magnetic field. So torque due to magnetic field in moving coil galvanometer will be NIAB, N-I-A-B. So in this galvanometer, we use a spiral or torsional spring like that. And this spring is connected to your coil. So what happens is that when magnetic field applies torque, then your coil will rotate, suppose in this direction, and this rotation will compress this spring. So at one point of time, torque due to spring will be equal to torque due to magnetic field. And when both this torque will be equal, then the coil will stop rotating. So at equilibrium, the torque due to magnetic field will be torque due to spring. So at that point of time, I will be equal to K upon B and A into theta. So we can also write I to be equal to G theta, where G is your galvanometer constant. And remember, more the deflection, more will be the current. So if deflection is more, the value of current in the coil will be more. So K is basically spring constant or torsional constant. B is magnetic field due to magnets. N is number of turns. A is area of coil. So all these parameters can be measured. So K upon B and A will have this value, and we can calculate I with the help of theta. So this is working equation of galvanometer, moving coil galvanometer. So at equilibrium, remember, at equilibrium, the torque due to magnetic field will be equal to torque due to spring, and the spring is basically in this shape. So we also call this as torsional spring. Now there are two important parameters. One is current sensitivity. So current sensitivity is deflection per unit current. So theta upon I. On the place of theta, I can put NIAB by K. I and I will get cancelled out. So current sensitivity is basically NAB by K, where current sensitivity can also be written as deflection per unit current. Okay, so you have to remember this equilibrium equation to get this formula. But remember, if N will increase, current sensitivity will increase. If A will increase, current sensitivity will increase. And B will increase, then current sensitivity will increase. But if K will increase, then current sensitivity will decrease. Similarly, there is one more parameter, that is voltage sensitivity. So it is basically deflection per unit voltage. So theta upon V. So on the place of theta, I'll put NIAB by K. I and I will get cancelled out because V is basically equal to IR, that is Ohm's law. So it will be NAB by KR. Suppose if someone asks you what will happen when number of turns will increase. But remember, if number of turns will increase, then length will increase, because suppose we have 3 number of turns and suppose we have 6 number of turns. So if we'll increase number of turns, then length will increase, and if length will increase, then resistance will also increase. So if number of turns are increased, then resistance will also increase, and both this will negate their effect. So if someone asks you what will be the effect on voltage sensitivity if number of turns are increased, no effect. So if number of turns are increased, there will be no effect on voltage sensitivity. Current sensitivity will increase, but voltage sensitivity will not change, because if N will be more, then R will also be more. So both will cancel out each other. Okay, so on the basis of today's lecture, I am sending you a quiz to solve on moving coil galvanometer. If you have any doubt, you can send me.